In today's video, we're going to talk about the superposition principle, interference, and standing waves. So let's start by the core principle, superposition. The superposition principle brought up by the question, what really happens when two traveling waves through the same medium meet? Do they smash into each other like billiard balls, or do they annihilate each other? The answer is way simpler than that, and it's called the principle of superposition. It just says that when two or more waves overlap, the new height of the medium at any point is just the sum of the individual's wave height. And that's it. You must add them up together. The odd rule about the two objects not being in the same place at the same time just doesn't apply to waves. And in fact, you can have a ton of waves all occupying the same space. Think about it. Like, for example, you're in a room with your friend with two different people talking, and you can hear both of their voices at once. Your eardrum is vibrating based on the combined pressure waves from both people, and the sound waves didn't crash into each other. They passed right through, and their effects simply add up. So if I want to give you a better visualization of how does it look like, imagine a rope. And we have a wave called y1 traveling to the right, and we have a wave called y2 traveling to the left. And now, what happens to them? As we said, the superposition principle says that their height is going to add up. So it should look like this. They're going to add up together. They're having interference. And then they're going to completely add up. This wave is y1 plus y2. And then the funny part is they're going to just move their weight like it's nothing has happened. And for example, this example would be like this. This is our y1, which is going to the right, and y2, which is going to the left. And now, the reason this works is thanks to a property called linearity. For the kind of waves we study in the introductory physics, the medium they travel through respond linearity. This basically means waves can pass through each other without getting wrapped or changed. Okay, so now that's just one example of the interference. So now let's try to imagine this. Imagine you have a single upward pulse down a long rope, like this, for example, like y1. It has a certain amplitude. We have a certain amplitude here, and we have a certain height. Now from the other end, you send another identical upward pulse. Like, imagine y2, but with the identical amplitude or height to the y1. As they get closer, they start to overlap, like here. And at the exact moment, they're in the same spot. Superposition tells us that their height should add up. And since both are positive, the rope at the spot jumps up to a height that sum of the two if they're identical. The pulse is momentarily twice as high if they're two identical. For example, it's the same as the example that I just said. So if we have y1, and let's call this, since they're going to the right, and since y2 is identical, let's call it y1 prime goes to the left. And when they get close to each other, for example, let's call this moment 1, moment 2, moment 3, and moment 4. At moment 3, when they collide and they get collided with each other, at moment 3, their height would add up. That's what superposition tells us. It would be y1 plus y2, just like as we have here. And the mind-bending part is after they overlap, they just keep going as if nothing ever happened. Like this, at moment 4, we can see. They pass through each other, emerging on the other side completely unchanged. So there's another question comes. What if we send an upward pulse from one end and a downward or inverted pulse from the other side? We still just add up their height. As we said, it's the principle of superposition says that we just have to add them up. And but this time, when we're adding a positive number to a negative number, we would have like a zero or destructive interference. And now we're going to talk about it more and later on. So let's say if their amplitudes are equal but opposite, for that single instant, they perfectly overlap, and the sum would be zero. For example, our y1 is going to the right with an upward pulse, and our y2 is going to the left. Just it's not identical. Y2 going to the left with a downward pulse. At moment 3, the sum would be zero. That is what you will see if you try to do this experiment at your home. So that's exactly what the superposition principle says. And exactly just like before, the rope goes completely flat, and then just like before, they emerge and continue on their way totally unaffected by their encounter. And the simple idea of adding waves displacement is the key to everything else. Like that, in math terms, if you have two waves, for example, we call it y1. So let's have d1 wave and d2 wave. The total displacement, it's just in terms of math, the total displacement would be d, the total displacement. And it's just x and t, xt. d1 equals to the d1 x and t plus d2 x and t. This simple principle is the foundation of everything that comes next. So now, we're going to talk about the interference or building on the principle. So what we just saw with the rope pulses has a name. It's called interference. Interference is just what we call the result of waves superposing, and it generally comes into two flavors, constructive and destructive. So let's write them down. First, we start by the constructive interference. And then we have destructive. Okay, first up, constructive interference. This is exactly what we saw when our two upward pulses met, like this example and this example. This is the constructive interference. But the problem here, not the problem, the fact is here, we have a constructive interference here, and we have a perfect constructive interference here. When they are like, the two pulsars are same as, like equal in every aspect, and when they add up to each other, it's called the perfectly constructive. When they are in phase exact, to be more precise, and there is no destructive between the waves, so it's called perfect constructive interference. So this, what we saw when our two upward pulses met, was a constructive interference, and constructive interference happens whenever two overlapping waves are trying to move in the medium in the same direction. And when we're talking about the continuous wave, like sinusoidal waves, this happens when the waves are in phase, as I said. That just means that the crest of one line of one wave line up with the crest of the other one. For example, this is the crest of one, and there is a crest of the other one, and they are lined up with each other. And also, the trough of the other one, the trough of one lines with the trough of the other one. And when that happens, their amplitude will add up, creating a new wave with much bigger amplitude, just like the one that we saw here, like this, which is much bigger, for example, than this one or this one. And if we have like the same two waves, the new amplitude would be double the original. Now, it is important to know that the wave intensity is proportional to the square of its amplitude. So, for example, if you double the amplitude, you're actually quadrupling the intensity. We're going to talk about this more later on. And this is why two speakers playing the same sound in phase will create louder spots in a room, and that's constructive interference in action. So now we talked about the constructive interference. Now let's go for the destructive. The destructive interference is what we saw here. It happens when our upward pulse meets our downward pulse. Destructive interference is like, if I want to describe it in a general statement, it would be when two waves are trying to move the medium in opposite directions. For continuous wave, this occurs when they are out of the phase. It means the crest of one wave lines up with the trough of the other one. For the constructive, we have the crest of one wave lines up with the crest of the other one, or the trough of one lines up with the trough of the other one. But now we have the crest of one wave lines up with the trough of the other of another. And here the amplitudes subtract. The resulting wave amplitude is a difference between the two. For example, the difference between the two here, this one and this one, since they had the same amplitude, so the difference was 0. So when we subtracted them, we got 0, and that's the resulting wave. They can completely, so when they can completely cancel each other out, it would lead to a moment of 0 amplitude, and we call this, like this one, a perfect destructive interference. This one, like the destructive interference, it is not just some abstract physics idea. It's a core technology inside your noise cancelling. For example, your noise cancelling headphone. This is your headphone, and you are listening to. There is a sound coming from outside to your eardrums. What your noise cancelling technology do? There is a tiny microphone outside the headphone, and the electronic inside instantly creates a new sound wave that is perfectly out of phase with the incoming noise. For example, if this would be the wave that's coming from outside your eardrum, what that a noise cancelling would do, it would try to create a wave like this. So the result would be in a straight line, and you would hear almost nothing. This new inverted wave is then played through the headphone speaker, and it destructively interfering with the outside noise, as we can see. It doesn't cancel everything. It cancels a lot of it before it can get through to your eardrum, and all your left is your music playing against a background of engineered quiet. And the reason why it cannot cancel every wave, it's because in real world, waves are rarely perfectly in phase or out of phase, and most of the time you get a partial interference for the new amplitude is somewhere between the maximum and the new minimum possible. And let's go for the standing waves again. We can take these two ideas and put them together to get a real payoff. So like, we've seen what happens when the pulses meet and what happens with two continuous waves. But what about very specific and common situation when a continuous wave interferes with its own reflection? And this is exactly what we see. This is exactly when something incredible happened, and that's what we see on our music instruments. So, and also this is how a standing wave principle was born. Think of a guitar, for example, tied down at both ends. You pluck it. That sends a wave traveling down the string. When the wave hits the fixed end, it reflects and travels back to the opposite direction. This is a guitar. It fixed at both ends. 6 string is, I'm just drawing like the 3 end of it, and it fixed. And we're going to call this, like, what do we call them? Nodes, and the waves, and the maximum displacement antinodes. We're going to talk about it. Okay. So as we said, when we try to pluck it, The wave hits the fixed end, goes down, it hit the fixed end, it reflects and travels back in the opposite direction. So now we have a perfect setup. Two identical waves, this one and this one, same frequency because it created by that, by ours, so it's the same and it's just a reflection of that one, and amplitude moving in the opposite direction in the same medium. As the original wave and the reflected wave pass through each other, they interference, but the result isn't a wave that moves left or right anymore. We hear it's going to the left, but it's whether, like for example, y1 is going to the right or y2 going to the left. But here we don't have that movement. This interference pattern itself becomes stationary and just oscillates in a place. It's more of an oscillation of the, or like the traveling wave. That's why we call it a standing wave. It doesn't really transport energy from one end to the other. The energy is almost like trapped in that oscillation. And if you look closely at the standing wave, you see two features. So let me just give you an example. For example, when you go to the laboratory and try to do this experiment, what you will see is just like this. Something like this. You will see that. It seems like that it doesn't moving. It's just oscillating. It just goes up and down. And that's exactly why they call it the standing waves, because you cannot see its movement. So there will be some spot with zero movement. Like here, both ends, here and here, which are called nodes. Nodes are the location of constant perfect destructive interference. If you remember, destructive interference means like when two waves are cancel each other out. And when we have a perfect destructive interference, it's when we don't have any wave left. The waves will completely cancel each other out, just like the nodes that we have here. At this point, any upward pull from one wave is always cancelled by a downward pull from the other wave. For example, here, just like the guitar example, the wave's going like this, reaches the end, and that's the reflect of the wave. So when they meet, this one is going, okay, and when they meet, something like this would happen and they will cancel each other out. So this spot would call it a perfect destructive interference, and then we call it a node. Okay, then halfway between any nodes, you'll find that are oscillating with the biggest possible amplitude. These points of maximum displacement are called antinodes. Here, this one is. These are nodes, and these are antinodes. Antinodes are the result of constant constructive interference, where the crest always meets crest, and the trough always meets trough. The trough of this one, like for example here, meets the trough of this one, so they would create a constructive interference, and it would be like this. It would create an antinode, just like the one that we have here, and there would be a node, just like this one. And the distance between one node and the next, or one antinode and the next, is exactly half a wavelength of the original wave. Okay. Now let's try to visualize it and using the equations. So this is all captured in a really neat equation. If you have two traveling waves moving in the opposite direction, okay, so when they're moving in a different opposite direction, we change the omega t. And now, if you remember the formula equation for this for the wave, for example, our wave one would be a sine kx minus omega t, and the other one, since they're moving at the opposite direction, the other one would be y2 equals to a sine kx minus plus omega t. And if you add them all together using the superposition principle, a trig identity helps simplify the sum to... Okay, let's just first talk about that trig identity. There is a simple trig identity, which says that sine alpha plus beta plus minus beta equals to sine alpha plus cosine beta plus negative plus minus cosine alpha sine beta. And we have it for cosine 2, but now we're talking about the sine. So the resulting formula for our wave would be y equals to the 2a. Let's put it on 2a sine kx times to cosine omega t. And now we're going to talk about what does this formula says. Let's look at the equation. It tells us everything. The cosine omega part just means that every point on the string, this part, that every point on the string is oscillating up and down over time. If you remember the formula for an oscillating particle, the formula was x equal to the a cosine omega t. And now that's exactly what that cosine omega t tells us. Again, it says that every point on the string is oscillating up and down over time. And the interesting part is the term in the bracket, 2a sine kx. This whole term acts like the new amplitude. So this one, 2a sine x, is actually our new amplitude. And you can see that it depends on the position of x. For any position of x, where sine kx is 0, for example, sine kx is 0, the amplitude will be 0 too. So the amplitude would be 0 if our sine kx would be 0. It would be 0 too. And those are the nodes. And for any position x, where the sine kx is equal to whether kx positive negative 1, the amplitude is 2a, which means that the maximum possible. Those are our antinodes. The equation itself is split ver from the when, which is the mathematical fingerprint of an standing wave. So now, let's go for the application examples. This isn't just a math on a whiteboard, and it's the core physics behind almost every musical instrument that I've mentioned before. Let's go back to the guitar strings. Since the string is fixed at both ends, those ends have to be notes, as we mentioned here. Notes here. And they can move. This physical requirement or boundary condition means that only very specific wavelengths can form stable standing waves on that string. The string length, L, has to be perfectly fit, an integer number of half wavelengths. You would write this down as L equals to the n lambda half, where n is any positive integer like 1, 2, 3, and n can be 1, 2, 3, and so on. From here, we can actually calculate the frequency, the notes you hear, and let's try to visualize it first before we get to the calculation part. So the physics behind it works like this. Let's say we have a standing wave here, and we have one big giant antinode here. This is our antinode. We have one antinode. And then we have two nodes. In here, this one is our n equals to 1. And our L would be half lambda. We can just look at it. And then we can say, okay, we have one antinode, and this one is n equals to 1. So our L is simply half lambda, or we can use a formula. L equals to 1 lambda over 2, which means that L equals to half lambda. And okay, the n equals to 1, again, we can talk about it later, but let's just talk about it. There's a first harmonic frequency we call at 100 hertz, and we call this the first harmonic frequency. And now we can go for the next possible wave that we can have for n equals to 2. It would be something like this. Sorry. Would be something like this, and we have n equals to 2. In n equals to 2, if we put our formula here, L equals to the n lambda 2, L equals, our n is 2, lambda over 2 gives us L equals to lambda. And that's it for this one. We have a second harmonic, which is 200 hertz. Then we get to the third harmonic, or n equals to 3. And sorry, something like this. And in our n equal to 3, the L would be, using the formula, L would be 3 lambda over 2 equals to 3 over 2 lambda, which is our L. And I want you guys to notice something. We have 2 nodes here and 1 antinode for n equals to 1. For n equals to 2, we have 2 antinodes, and we have 1, 2, 3 nodes. 3 nodes. And for n equals to 3, 1, 2, 3. We have 3 antinodes. And we have 1, 2, 3, 4. 4 antinodes. So notice something. The number of antinodes is equal. Antinodes equals to the number of our n, and nodes equals to the n plus 1. So now, let's go over the equation now. First, we solve the equation for the wavelengths L. This tells us that which wavelengths are physically allowed to exist under the string. Using that formula, L equals to the n lambda 2, we can derive for our lambda. The lambda n would be 2L over n. And the little n just reminds us that there is a different wavelength for each integer. And now, how do we get the frequency? We need the universal wave equation. Speed equals frequency times wavelengths, as you guys already know. V equals to F lambda. And the speed is determined by the string's tension and thickness. And we use the formula for V in a string, tension over linear density. And if you want to drive F would be V over lambda. And finally, if we substitute our allowed wavelengths into this equation, this gives us the equation for every possible natural frequency that this string can produce. Fn equals to the n V over 2L. And as we said, V can be in a string. V is equal to the tension over linear density. So our formula would be n over 2L times tension over linear density. And we can use this formula to find every possible natural frequency. And let's use that formula for a quick example. The simplest possible pattern is when n equals to 1. And this is called the fundamental here. F equals to 100 Hertz. It's called the fundamental frequency or the first harmonic. Using the formula, its frequency is F1 equals to the 1, we said n1 over times V over 2L or just V over 2L. This is the lowest node that a string can play, with nodes at the end and one big antinodes in the middle. The next pattern is a second harmonic when n equals to 2. Here, it's 200 Hertz. This string fits one full wavelength, creating a new node in the very center here. And its frequency can be calculated through F2 equals to, we can find the V now, and if you had L, and F2 equals to the 2 times V over 2L. And that's exactly how the video try to find the frequency. Sometimes in an example they would give us frequency and the length, they would ask for the speed, or sometimes they just want the wavelength. And this is exactly the double, like here we have the double of the first fundamental frequency, which means that it's again double and 200, but in the musical and in the musical terms, it's called an octave higher. And when you pluck a string, you're actually exciting a mix of allowed standing waves that are allowed in that frequency. Okay, now let's go over this example. It says, before that, pause the video, try to solve it, and check your answer with mine to see if you get any of the understanding wrong or right. It says the top string on a guitar has a fundamental frequency of 330 Hertz when it is allowed to vibrate as a whole along all of its 64 centimeters length from the neck to the bridge. A fret is provided for limiting vibration to just the lower 2/3 of the string. If the string is pressed down at this fret and plucked, what is a new fundamental frequency? How can we approach this problem? First, we have to identify our values that we have. So first, let's start by, it says that along all of its 64 centimeters length. So the original length is L1 is 64 centimeters, and our original frequency says is 330 Hertz. Now the new length after plucking the fret is 2/3 L2 equals to the 2/3 of our L1, which is 64 times to the 2/3, and it would be 42.67 centimeters. So now, how can we find this new frequency? The fundamental frequency of a vibrating string is inversely proportional to its vibrating length. And so if the length of a vibrating part of a string is decreasing, the frequency will increase. And the thing that I've just said is derived from the formula that we just talked about. F equals to the NV over 2L, considering that the V doesn't change, so it would be N over 2L. And now let's see, if we increase the L, the F would be decreased, and if we decrease the L, the F would increase. So now looking here, we decrease the L. So what do we expect here? We expect for the frequency to increase. Now let's put it in a formula. If I want to put this state that I've just said mathematically, it would be that frequency is inversely proportional to the length And if we want to put it in a formula, our F2 over F1 equals to the L1 over L2, because it's inversely proportional. It's not going to write down here. So let's put our values in. So we want our F2. Our F1 is 330 hertz and our L1 is 64 centimeters and L2 is 42.67. So what is our F2? F2, we just have to put the values in. We can simplify 64 over 42 by 3 over 2 because we just said 64 over 42, I'm sorry, 42.67 over 64 is 2/3, so 64 over 42.67 is 3 over 2. And then we can just calculate it to be 400, why am I writing 2? 495 hertz. That's our new frequency. And as you guys expected, the frequency has increased because we lowered the length. And now let's go over another. Okay, so now let's go over another example. This one might be a bit challenging, but it's still easy. You just have to understand what it wants, and understanding the concept would help to make it easier. So again, please pause the video, try to answer it, then check your answer with me. It says one end of a horizontal string is attached to a vibrating blade and the other end passes over a pulley. A sphere of mass 2 kilograms hangs on the end of the string. The string is vibrating in its second harmonic. The sphere is then replaced with an object of unknown mass. The string now vibrates in its fifth harmonic. What is the mass of the object? There is something that we need to consider. First, which formula for frequency should we use? We should use this formula. Fn is equal to the n over 2L times T over mu, linear density. And what is T here? T is mg. Okay, so let's talk a bit about the formula. Fn is our frequency of nth harmonic. L is this length of the string. Mu is the linear density, linear mass, linear density, which will be assumed constant because we have same string here, and T is the tension, which can be calculated, which is again depends on the mass hanging. And now let's call it. Let's call what do we have in what the question gave us. The M1 is 2 kilogram, and it's in the second harmonic 2, and our N1 would be 2. M2, we don't know nothing about it, but would be in its fifth harmonic. So from the equation that we just said, what are the constant here? We have the same string, so the linear density, linear mass density would be constant, so they would cancel each other's out. We don't need it in the formula. The L again would be constant for both the strings, so we don't need that too. So our Fn would be proportional to n square root of t equals, and in which the t is equal to ng, and n is square root of mg. And again, we don't need g. We can cancel g out because all of them have the same g. They are in the same planet, so g would cancel out. And now let's compare the two cases. We have F2 over an F1, in which that 2 equals to N2 square root of M2 over N1 is square root of M1. But here's the catch. The point here, the point of the question is, how do we know the relation between F2 and F1? Like it says, it is attached to a vibrating blade and the other passes over a pulley. So we didn't change that vibrating blade. What it means is that we have the same frequency. We didn't change the source. It's the same vibrating blade, and the driving frequency is constant. So F2 over F1 is equal to 1. F2 is equal to 1, and N2 square root of M2 over N1 square root of M1 will be 1 too. And now if you plug the values that we know, 5 times the square root of m2 over our second harmonic, or square root of 2, would give us, should be equals to 1. And if we try to solve it, it would be it would be 0 point, our m2 would be 0.32 kilogram. And there was another way to find it. Mathematically, we could just say, okay, so now square root of m2 equals to 2 square root of 2 over 5, and then we can power them to the 2, and m2 would be equals to 4 times 25, 5, 4 times 2, 8 over 25, which is 0.32, and that's how we could solve it. So now, let's talk about another simple example. It says the string is vibrating as its fundamental frequency. What would be its fundamental frequency if what would be its fundamental frequency if the length of the string is double with all other factors are held constant? Again, what was the question? What was the formula for finding the frequency? F equals to 1 over 2L square root of T over mu. We didn't change tension. We didn't change the linear density. We just changed our length and we doubled it. So what it means that instead of 1 over 2L, we have 1 over 4. So our new fundamental frequency would be, if this is F1 and this one is F2, our new fundamental frequency would be half of the original frequency. If this explanation helped things click for you, think about subscribing for more university level physics breakdowns. I hope you guys enjoyed the video, and if you have any further questions, you can ask it in the comments. Thank you for watching. Please like and subscribe.